from assignee from Texas Instruments, and today I'm going to talk about a little time-sensitive networking and driver requirements and kernel modifications required for that. So, what is time-sensitive networking? It's a set of standards developed by a time-sensitive networking group in order to guarantee bandwidths for appropriate streams through all nodes in the network, and allowing us in the same time to exist regular traffic in this network. To implement it, it requires a bunch of standards implemented on every node in the network. And initially it was based on AVB. AVB contains also some standards and some requirements for latencies. And this is what time-sensitive networking actually do. It's guarantee latencies through network. So what benefits we have, and if we use one network for different devices, we can have less number of cables, and we can have a lot of different streams through this network instead of enormous number of point-to-point cables. And the same network can be used for different purposes, like we can have some audio, some video, and some different sensors, and all of them are connected in the same network. It's a simple example how it can be used. Instead of car can be any factory or big car or something else that just includes a lot of different nodes. It can be cameras, audio sources like microphones, speakers, some sensors and stuff like this. So it can include in one network a lot of different types of devices that requires. Here we can show some simple example like an audio and video networks requirements. For live audio performances, we need a maximum delay between musician doing something and we hearing something on another side. This can be up to 10 milliseconds, and we can hear this difference. And we can have we have some latency, some delays when we handle packets in different DSPs. It's plus mixer delays, plus more DSP delays, and all of this is up to 8 milliseconds. So we have 10 minus 8. We have up to 2 milliseconds for networking, and it's a worst case that we can have. So also one of the requirements is we need to have synchronized time sources for all nodes in the network. And the difference between the jitter between those sources of timestamp can be up to 10 microseconds. And but TSN requires, and it easily can be achieved up to 1 microsecond. Also, we have some requirements for control loops. It depends on the situation, but it also can be some small delays that should be guaranteed through this network. It should be determined exactly. We can't, be up at those latencies. Next slide. And what hardware requirements for every device in the network? It's very important to have timestamping hardware on every Ethernet switch in the network. It can be software done, but it's not will be very accurate. So it's one of the main requirements, and it's required for both as a sender, as a receiver, because it required by PTP protocol or other protocol that can be used to synchronize time sources. Without this, we can't do this. We need to have credit-based shaper or time-aware shaper or some other kind of shaper that just guarantee us needed bandwidth and allow us to send frames frames that have definite size. But this requirement is only for sender. Receiver, not required for receiver to have any shaping. And all this network can work only within some TSN cloud. That means that every node in this network must be TSN capable. So it should support a bunch of protocols that allow us to do, deterministic, to have deterministic latency for every hop. And also, I just didn't. We have an. One of the requirements can be also VLAN support on receiver side, when we can have ability to split incoming traffic in different channels based on VLAN tag. So it also allows us to handle packets and take them from different queues. This is a list of standards that actually can guarantee us those TSN networking and the time synchronization protocol that basically currently is implemented using PTP version 2, but it can be any other protocol. There's no any requirements for that. And it allows us to synchronize, to contain one time domain with where every node in the network has the same world time. It's very important for AVB, for instance. For some cases it can be important, but for AVB it's very important. Also we have a forwarding queuing enhancement that is requirements for credit-based shaper and other protocols. One of the important protocols is also stream reservation protocol that allow us to reserve resources on every hop, and using this protocol we can set a network for appropriate streams for classes of traffic. It can be a very complex system. For instance, we can have several hops that have a lot of streams flowing in different directions, and in some cases we need to combine those traffic, like multicasting between some nodes, just saving bandwidth for other purposes. Next slide. When it was AVB, because AVB was as a start for TSN, the devices that transmit packets were called talkers, and receivers were called listeners and bridges. So we have now names for TSN as transmitters and receivers. As I said, the requirements for talker and listeners are different, right? It's a credit-based shaper for sender and such requirement for listeners. But the primary requirement for listener is capable of buffering the amount of data during the time period equivalent to accumulated maximum jitter that can be calculated by difference in time stamping and measuring propagation time of packet between two nodes in the network. Also, TSN streams will not use more than 75% of a link bandwidth. That allows us the same network to use for other purposes like data, any other kind of data that doesn't require AVB regulation. So, and we leave in remaining capacity for non-TSN streams. So TSN uses three levels of identification. It's a stream ID that is unique through all over TSN network. It cannot be the same for some other cases. It's just unique name, and usually it's randomly assigned. Also, we have traffic of class that is identified. It's used to different traffic with different latency targets. For AVB traffic, for instance, for class A, we have target 2 milliseconds, right? Which is And also we have for UB classic B traffic that is maximum latency, it's 10 millisecond. And also we have some, it'll be next. And yeah, we have stream destination address and other parameters. So it's a simple picture that allows us to a little imagine how it works for a simple case for TSN. We have stream shapers on Docker side. We have an Mac class shapers, class A, class B. Class A is 2 millisecond requirement for delay. Class B and best effort traffic. We have switch that split this, and we can send this traffic to different end stations. And it can be, as an example, when we have some microphone and remotely speakers can be situated in different places, and through different number of hops, and the latency for every of them is different, right? So to reproduce music or some else synchronously on both speakers, we need to have an ability to synchronize them. They should be played in the same time. So, this example is how we split this traffic between the network. We, using a stream reservation protocol, just reserve bandwidths and latency requirements on every hop through this path, and that allows us to don't worry about congestion and other stuff that can broke our latency. This is the main goal. The main protocol is just allow us to reserve these resources. It's a stream reservation protocol that registers streams and reserve bandwidth and other parameters that can be needed for reserving and guarantee latency per hop. How it identify every frame in the network? It uses PCP codes in VLAN target to split this on different traffic classes, and different traffic classes has its own parameters like latency. We have a bunch of protocols like MRP, MSRP that allow us to do this from user space. Yeah, here we can see a table that just declare requirements. We have also one of the main parameters here is the observation interval for class A. That means we send packet every 125 microsecond. Default priority is PCP codes, exactly like it is in VLAN tag. And maximum transmission time, it's a worst case when we send packet to outside. Basically, we have for AVB, we have two classes of traffic, A, B. For TSN, this number of classes can be different and can be much more. And when we traverse it to TSN, actually here one additional class of traffic, standard class of traffic, it's control data transmission, CDT class of traffic, and requirements is reservation time is about 500 microseconds, and maximum transmit time is about 100 microseconds per 5 hops. Also, we have for AVB traffic, we have transport protocol, AVBTP. This is an example of this is a net frame, and here we can see we have VLAN tag that contains class of traffic in PCP field, and we have stream IDs that exactly identified within one network. We have AVBTP timestamp that is wall time, understandable on every node in the network. They have the same time within 1 microsecond jitter between them, so we can suppose that they're exactly the same. And we have samples. Timestamp is only for first sample. Those samples can be as in some different channels as in the same sample rate. Also, very important is precise synchronization protocol in our case that allows us to synchronize two sources between and to sources, and it should find out the best clock in the network that can be used and with best accuracy. And yeah, next slide. So, it's used best master clock algorithm to identify best clock source in the network. And once this clock is identified, it just starts synchronization. And the main requirement here is exactly timestamping hardware support on every Ethernet card. So it allows us to measure, propagation delay between two nodes, and using some simple filters or Kalman filters to identify exact and average propagation delay, and figure out and synchronize time sources in different places. And then periodically we can send sync messages that allow us to keep it in sync between nodes. And the final result is all PTP nodes are in sync in the same wall clock time with 1 microsecond accuracy over 7 network hops. Usually it's about 150 nanosecond. Also, I saw results that can be achieved is up to 50, 60 nanoseconds time shift between time sources. This is a simple example how, for instance, some audio traffic can be looks like in a VTP protocol when we send it from source to destination. Here we have wall time. It's the same absolutely wall time that was synchronized with PTP protocol. Then we have some stream rate, and we have a timestamp that are timestamp in wall time. It's like in conversion, like in, who knows, in ODP, local time to global time to local time. It's the same, but in hardware. So we just need some, known frequency that can allow us to figure out what exactly time is. So the picture. Most Ethernet subsystem have timestamping model currently, so that's not a big problem. So, and they can have link shapers, credit-based shapers. That's hardware shapers, not software. We just put those in different transmit queues. We have several transmit queues. We set those shapers and send packets to those queues, and the other job is not our concern. The hardware stream shapers also can be present in the Ethernet card, but it's usually implemented at DMA level. And then they are redirected to link level shapers. But all of them can be implemented in software shapers, so they should in some ways coexist with each other. And every shaper requires to be configured before usage, right? And we need some, in kernel, we need some interface to configure shapers. We can use some simple case using some, TC utils or stuff like this, just to, some Ethernet tools just to configure those bandwidths, shapers, and send this some traffic. But it's hard to collect every requirements for every stream that is taken from stream reservation protocol to, and it should be placed that hold all this information in order to set link shapers. And just, integrate every requirements and set shapers. Should be some place, because sources of traffic can be in different places here. In some cases, it can be in user space. In some cases, it can be directly in kernel. In some cases, it can be with DMA just directly sent to the net card if we know some format of packet DMA. If there is a net card inside of some COC, understand this. Yeah, so I've said link level shapers present classes of traffic, and yeah. So next slide. Значит, presented raw new TSN subsystem from Cisco. Where said recently, patch set that adds a new TSN core with possibility to add new shims, and it's like we can have different shims that just allow us to send from different subsystems in the kernel directly to Ethernet cards with some layer that allow us to connect them. It's called shims in those patch sets. So also it adds raw TSN shim for ALSA framework, but it works only for playback. And this adds also raw TSN shim for TSN net that allow us to handle operations toward the networking layer. And SysFS interface that create, control, configure streams and show current state for TSN core. And also tracing and some support of TSN for TSN for Intel i210 controller. Also at this moment added support for TSNs, support for stream shapers for CPS-WTI controller, added multi-channel support for CPS-WTI control, and ongoing support for link level shapers for CPS-W and netcpTI drivers. CPS-W is one of the drivers that used in many boards like Wigglebone and others. So, but not every revision contains possibilities to set shapers. So it's some kind of, when we're adding some support to that, we need to test on every board. netcp driver is a driver used mainly for Keystone boards. And actually we are going to add this support only for K2G board. That is, will be all the stuff will be upstreamed after TSN core will be stable enough, because in this at this stage it's not it's under RFC and it's not stable, and we need to change several interfaces to make it upstreamable. Ongoing multi-channel support also for netcp TI drivers, and we are planning to add, then after it will stabilized, we plan to add TSN support for CPS-W and netcp as also for both, because partly CPS-W is a part of netcp driver. Next slide. So the main plan is add to a bunch of correction for TSN core. And currently configuration based on SysFS interface that is not correct. It's allow us for test. It's allow us to look how it works, but it's when we wanted to send it, we need to replace it with some other interface like netlink, like it's done with DCB from Intel. So also it has some drawbacks in hardware timestamping. We need to update transmit time using hardware timestamping, because in this moment that's not true. So we need to extend tracing capabilities accordingly, and we need to generalize a little TSN core, because it was written a long time ago. Basically it was AVB oriented. It was a little corrected, and at this moment just be some little other generalization about TSN core that allow us to set different classes of traffic, and add more general mechanism to set shapers parameters, because at this moment we just operate internal parameters of credit based shaper, but it can be changed, and we need to use some general mechanism like bandwidth and size of frame, and then using this information we can calculate internal parameters of shaper. Also we need to finish and test listener implementation and capture for ALSA driver. Add mechanism to use hardware and software stream shapers, Because in some boards in TI we have additionally hardware shapers for streams, but that's not considered but current implementation of TSN core. At appropriate support for Ethernet tool and others, so just a low level length. Any questions?
So TSN mode is set on a per interface basis?
Yes.
Okay. And can that include virtual interfaces, or is it just?
Yes, why not? Every, do you mean VLAN? Or support some, what exactly do you mean?
Well, you know, we've talked a lot about, you know, interfacing in virtual environments, VMs and containers and such. And so the question is, you know, is TSN's, you know, determinism require effectively real mode operation?
Yes, it requires real mode, but no, simple. It depends on the use cases, because in some cases we can have control loop, not audio, video, for instance, right? And we can have different requirements for this latency can be different. And for instance, if we have some virtualization, it adds some latency. We need to be sure that it's in within maximum worst case latency delay threshold.
So
At this moment, any plans for that?
So what I'm hearing is that depending on the tolerance that I need, because it sounds like from what you were saying that depending on the application, I may need as you know, little as 2 millisecond tolerance down to 1 microsecond tolerance. That, you know, the loose
1 microsecond. I don't know. The important thing that I just forgot to mention is that every this set of protocols are designed not depending on the media. So in our case, we're just using Ethernet, and my calculation is based on 1 gigabit Ethernet. So it can be 100 megabit. I'm talking about 1 gigabit. So maximum latency per hop in one it'd be up to 4 or 5 microseconds, not 1 microsecond. That's not possible.
for speaker synchronization.
This is different synchronization. This is not latency. This is not propagation latency. This is jitter between different time sources.
Right, you want the 1 microsecond is jitter requirement, not all latency.
Yeah, maximum. Worst case. Usually it's 150.
Yeah, well, there's some applications have both, some have just one. Like if you're a speaker, usually it's a jitter requirement because you can buffer as long as everyone buffers the same amount. Right.
Does TSN require real-time Linux kernel, or can it be done on normal kernel?
Actually, I'm considering a case when we can use it in Linux kernel, but it can be implemented in hardware. It can be implemented in any other operating system. That's
Maybe I had to add that, but at least I say typically both. So typically, if you have an RT patch, or if you want TSN, you want Linux, you usually want RT. But there's no strict. I guess that's about what you meant. There's no strict dependency,
But it's recommended.
yeah, or they kind of go hand in hand. If they want real time everything.
Are you plugging into the just ELSA or into the ELSA SoC? Because there is.
it's like a driver of ALSA.
Oh, okay, I see.
You said that one of the problems you need to solve is time synchronization of technologies. And you said that you need synchronization of systems, right? But maybe in this case, you need to say about synchronization ETP clock, which might not be aligned to system time. Because
Yes, why not? But usually it's aligned.
usually, on the platform, it's not. It's a separate clock of the
Yeah, this can be different because we can have clock timestamp on the. Do you mean timestamp on the Ethernet card exactly, right? It can be separate. No any requirements. You know, it'd be nice if we have some PLL that is adjustable. We can just adjust it, yeah, and yeah. It'd be better than just emulate this clock.
To synchronize to different clocks, especially different frequencies.
Yeah, we can just a little tune this frequency on another side and achieve our goals.
So you use timestamp and just to understand that you need to accept part of the drop time. It's too late to accept.
No, it's used to reproduce it. It's wall time. It's wall time, and it's exactly time when this sample should be played on another side. It just includes like we have a target, for instance, in 2 milliseconds, right? When we send this packet, we just add this delay, maximum worst case delay, to time, to wall time clock on our side, plus this 2 milliseconds, and we can be sure that it would be within one worst case. We can reproduce exactly in this wall time on another side because wall times are synchronized.
So you do buffering audio?
A little bit, not much, because we have, as I said, we have an target in 1 microsecond, right? But it's worst case. Actually, we can measure this propagation delay, and it can be less, right? We can, somehow figure out the average latency. Then we can differ maximum worst case with this latency, and we have some time to accumulate traffic, right? And this time is used to define the size of the buffer. It's not important. It depends on algorithm.
Do you account time for encryption with code?
It's real-time traffic. Any encryption, any decryption. Maybe it can be what, but at this moment I don't consider this case. It's yeah.
What kind of hardware support do you need for a full PSM solution? It probably timestamping, but anything else?
Yes, we need protocols, stream reservation protocols, just to, configure every node in the network to reserve stream. Because without this, we cannot guarantee any some congestion or another connected hop can broke our algorithm. So we need to have some mechanism that allow us to set every node in the network for appropriate.
Managers in the hardware? The question was hardware.
Oh, hardware, no. We need hardware. This is only for sender side. We need in hardware is some kind of shapers for every class of traffic. We can also have some hardware shapers for streams, but that's not important. We must have shaper for sender, timestamping on both sides, the sender and the receiver.
Quality of service on
That's the main.
side?
What?
You need some quality of service on the receiver side to speed up the reception?
It's actually when we set up. Do you mean hardware, right?
Yeah.
Actually, when we configure those shapers, we just already guaranteed about this because we can have different settings. We can have prioritized queues. One more important, one another. But can we when we reserve bandwidth for every class of traffic? That's not important because all is done within this credit-based shaper. We just said that it's some round-robin mechanism. It's not.
Once it's IEEE standards, several of them require hardware support. Some of them don't. But like preemption, if you're preempting an Ethernet range at the L2 level, that's hardware support.
Is preemption required, or is it function?
Well, there is no, those are individual IEEE standards, and a hardware product will follow some of them, probably not all. But I like to use that preemption as an example. It's pretty extreme. If you start preempting Ethernet frames, you are in a certain kind of world. Not everyone.
Yeah. Also, very important to talk about that. Also, we have some requirements for frame size, because frame size is interfering traffic, right? And the smaller is this size, then we have less latencies. So, for instance, for class A, for AVB, it's an about 256 bytes, and we, knowing speed of the media, can calculate the latency that required to transmit this packet. And this is like a small chain that chunk that interfering traffic.
So Pekka, maybe I didn't quite fully understand your answer, but it sounded like TSN is this large collection of IEEE standards.
Yeah.
Any given platform would support only a subset of those, but is there a certain critical subset that you need in order to say that you're a TSN system, or?
Think here it's kind of a hype word, so you can call whatever you want.
Right, the marketing label versus the technology.
So those IEEE standards, so I would say that what Ivan already said, timestamping has some sort of shaping. Unless you do those two things, you can't really call yourself.
But it sounds like there's different levels of application sensitivity that may require more of those standards rather than fewer. So,
Yes,
so
yes.
TSN is more of a continuum rather than a binary attribute for
Yes,
that.
yes, and then some of those are very, like if I have a switch in the network, I support them. But an endpoint, some of them are not so relevant. So
Right,
that's,
right.
Yeah, but that not all protocols they should be supported, like credit basic shaper or something like that. We can we have also requirements for stable latency per hop, not depending on topology, for instance, because we can connect to switch much more connectors, and in this case we can have a situation when this latency is increased. Also, we have a standard that define us and to support this latency stable.
Also, you mentioned 75% allocation. Is that a standard, or is that a best practices? Or?
This is standard actually, but no one allows you, to configure.
Well,
You can use more.
The standard rule is not in queuing there is don't go above 70%. Okay, so the fact that you can get 75 is impressive.
it doesn't, I think it's 75 in the resource reservation protocol somewhere, right? Right, I'm asking a little bit here, but it's like but it does, like you said, it doesn't mean that somebody's product, they'll always go 75. They might, some high-end audio might decide that 50 is about high-end as I could ever go, and somebody pushing the limits might go 90%. Don't care. Like you said, the reservation protocols allow you to. It's kind of a trusted network. It's not if somebody just plugs something in, you'll play the whole thing. So who doesn't play ball?
A related question to what you asked, Bill. Is there a certification process? Those automotive guys have a tendency to have okay, you have the bunch of standards, and then you have the tool to measure that your stuff is compliant.
Gold star.
And us, we will be doing, in LNG, we are doing this TSN. The question is, do we need to buy special tools to pass certification?
I would approach it from, I'm sure the automotive have various levels that they involve software and all that, but it's to be fair, it's IEEE Ethernet standards. So it's, once they get approved, they're standard features, so it's more like standard Ethernet test equipment. But it's, so some of those, like frame preemptions or some of the timing stuff, the equipment is pretty new and expensive, yes, I
I guess
there are a couple hundred.
UNH can help you there.
So bottom line, in LNG we will do the software, but members will take care of whatever.
Yeah, certifying their hardware level
Right.
features, but I think some level, let's try to measure what latency can we achieve with the Linux stack.
Okay.
And I think it's just really some of the numbers Ivan was quoting were kind of the audio guys have some of these exact that I can only have 7 hosts. I have a class, whatever you call it, class A and B. Those are like audio application constraints. Doesn't mean that another application follows the same.
So these are being developed as a series of kernel patches.
It's on from Cisco, right? And we have 2 versions already, and they just allow us to test it. They are not ready to be merged or something like this. It's just proof of concept. So at this moment, it just requires some review. Maybe someone wants.
So is there a timeline for when they'd be, ready for submission? Or
I'm not out of those pages, right? So I'm not aware that those pages. My goal is just to correct them to be appropriate for my hardware, right? So I'm just at this moment adding a support for TI drivers. After it's finished, I can continue work with TSN core. But in parallel, I can also review those pages, and that's my requirements to that.
Yeah, I think it's massive, but it's also some latency measurements that include software. So that would be kind of common.
That's all. Thank you.
Hi. So I'm going to talk about this ODP over PCI. This is an idea. There is no plan to develop such a thing. This is just for food for thought. I've been refining the idea since about a year. I had the idea not with ODP, with another background, but this translates very well in ODP. I think it's also a nice continuation from what Naranja presentation yesterday, where he presented a smart NIC and how the smart NIC has to interface with PCI to send its packets over PCI. So this presentation could be seen as another extension to that idea. And if I try to summarize it in a very few words, it's to expose an ODP smart NIC as a standard PCI device. As you have today, VirtualNet is a standard device in VMs. I would like to have a PCI device that I talk ODP to that device. And so this would mean that if I have a smart NIC coming from KVM, from NXP, from TI, from whatever, I would be able to leverage the hardware accelerators through one single device driver. I would not have to create as many drivers per. So it goes, let's say, virtualization a step further, and that's probably possible. I'm not even sure it is really possible, but that would be leveraging the ODP API very founding concept. Now, is it one single PCI device, or is it multiple PCI devices? For example, we could have a classifier PCI device, a scheduler PCI device, and
let's say, one PCI device per ODP functional block. That can be maybe one idea to go a step further on the idea. But what's important is to have at least one device which is a basic packet source. Why? Because it would be nice to have the Linux kernel, the TCP IP stack, be integrated with that, let's say, SmartNIC interface. And I've seen some big resistance by the Linux community to integrate acceleration support whatsoever. So probably we need a simple packet source device and some kind of offline control of the data plane. So let's say the configuration of IPsec offload, etc., is done out of bound from that particular device. Typically, when we think of I have different hardware, well, I can have different device drivers, and it masks the complexity on the application perspective. But if you look at NFV, the application life cycle is complex and long. You have what's called onboarding, so that's you describe your application with a VNF descriptor, you load that into the orchestrator, and then the orchestrator can deploy that application on the hardware. Now, you are very creative in pushing new products on the market. So if you have to change the driver for version 1, version 2, based on the new advances in the hardware, this would mean that the network operators would have to onboard constantly new versions of the VNF and make sure that they deploy the proper VNF version on that particular compute node. So it becomes very quickly a nightmare. And it looks like, you know, the DLL hell on Windows, where you have, okay, you can have several versions, but ultimately application fail. So having one single driver for multiple devices really tries also to simplify that problem for the network operators. At CNFV, there has been a concept based on what's called extensible para-virtualized devices. It's basically Virtio devices with some extensions. And the extensions are how can we benefit from, let's say, virtualization and hardware independence, but yet still have all the benefits of the hardware accelerators, have live migration, and have everything. It's not for free. So Virtio is nice, but it does not really fully expose the hardware capabilities. So instead of having Virtio Net, we could have ODP Net, which would basically do some form of Virtio for hardware independence, but that could also drive this ODP PCI device at the same time, so that if there are any hardware underlying, then the network stack could really benefit from the accelerators. And so what would be the consumer of that ODP PCI device? Is it an ODP application, or is it just the Linux kernel? Well, it should be both, so that the an ODP SmartNIC could be exposing its value immediately consumable by the Linux kernel. But at the same time, it could be an ODP application, and we would have actually two ODP instances, one running in the host, one running in the SmartNIC. They can work in a fully independent way. They would ignore each other, more or less. On the host side, you could see the SmartNIC as a packet I/O, but maybe over time, we may want those two ODP instances recognize themselves and do some distributed load sharing. I mean, who's doing what in the process. So we have one ODP that can autonomously do things on part of the traffic and can be used by the host ODP instance, maybe for more traffic handling, or just to pass through to another, let's say, line card, which is doing additional, let's say, outgoing traffic. And if I look at it from, if we're trying to do, okay, I said that this is an ODP PCI device, and this means that we would have to define a configuration space, and we would have to translate ODP API into PCI registers or memory blocks, and essentially this is ODP remote procedure call, RPC over PCI. So essentially, I've described this already. So as I said, this is something that I've briefly touched on last Connect in Las Vegas, and I wanted to formalize a little bit more the idea to be discussed later between ourselves. One reason also I've wanted to do that is that if the idea is good and if somebody wants to implement it outside ODP, and if later we want to do that, we don't want somebody to file intellectual property and prevent us to do that. So it was also a way for me to make sure that this is now a public domain idea. And as we're in open source, this is, I think, important to cover this aspect.
In this, I mean, you propose the host application to be actually aware of what's running on the SmartNIC, or you want to see it as an offload model where certain operations are transparently accelerated on the SmartNIC. But if it's really the awareness of another ODP entity running on the SmartNIC is present on the host side, then those applications may not be as portable as you would like.
So that's why I said I don't know if it's a good idea to have the application aware of the other, the one ODP instance to be aware of the other. It's unclear if it's a good approach or not. Probably the simplest way is to make sure that it's, let's say, a smart packet I/O from an ODP standpoint with some capabilities like IPsec inline acceleration and things like that. And if the two ODP instances are aware of each other, this probably mean it is an embedded application that the network equipment provider is effectively has defined hierarchical traffic handling, so it would do the proper integration of the two ODP instances, and maybe trying to do that in a generic way would be way too complicated, and probably not answering vendor A and vendor B requirements.
If you're dealing with an RPC interface, there's no implication back
idea of having a standardized virtual PCI config space for ODP device, which can advertise capabilities. I think that's what I think is then the ODP app is targeting a generic device which is advertising its capabilities, and then whatever acceleration it's capable of gets leveraged. That's the idea. So for portable applications, I think that's really important. But there are certainly a lot of use cases where people know the split between the NIC and the host. So that's a reality as well. But whether you can standardize that is a challenging problem.
To make it standard, it's like previous presentation was before they use Word to compile some logic, and after they upload it to the code. If we go this way, but it's like application, it's like not hardware application. But actually it's might be a good use case for virtualization. If you simply inside VM do some network application like network layer 2 forwarding or maybe NAT to do some other translation. And you know that you have somewhere some smart NIC under there. Then you can use some small code which you completely upload to this smart NIC. Smart NIC will do everything. You even don't get any actions to this VM. So VM will just configure all of this stuff.
Yeah, that's interesting. I think there needs to be a proposal that goes to the next level. I think what you're saying is definitely
I think also to be consistent with ODP spirit, this, if we do such an interface, it should not define the actual packet descriptor and queues. That, even though we can standardize, let's say, access to the packet I/O, if we ever do that type of thing, we should be able to let that to the hardware creativity. Standardizing is good, but sometimes we have to define exactly what we standardize. For example, having a metadata or would be probably a bad idea. I mean, standardized metadata. Well, I guess this can be also discovered as a DPA2 device. I mean, the way to, we can probably do many different flavors of that type of, providing that the interface is defined. So I think. Yeah, we can. Yeah, that would be one way to simplify consumption by the Linux kernel of this ODP device. And if coming back to the discussion we had yesterday with Naranja, the idea to have the ODP SmartNIC deliver the packets directly into a Virtualnet buffer structure on the VM is, I think, a game changer, because you have hardware independence, you have zero core consumption on the host, and you have rich, let's say, acceleration from the SmartNIC. So.
I think the biggest benefit here would be the
we have to have mandatory supported types of things, otherwise migration is, yeah. Yeah, yeah. Right. So it looks like a further activities for ODP cloud profile definition. Well, I think we're already over time. Thank you very much for attending all the LNG sessions this morning, and looking forward to talking to you in other context. Thank you very much.